Alright, in this video I want to look at how to solve quadratic systems using the elimination method. This is a method you used when you learned how to solve systems of linear equations in Algebra 1. You learned graphing, substitution, and elimination. Elimination works very well for linear systems. It does not work as well for quadratic systems, which is why it's somewhat de-emphasized. I'll remind you of what elimination looks like with linear systems if I just pull in this problem right here. 5x plus y equals 8, x minus 3y is equal to 24. The idea of elimination is to multiply one or both equations by some constant so that when I add the two equations together, I eliminate either the x's or the y's. Usually this is pretty obvious. In this particular set of equations I have right here, I have 5x and x, I have plus y and minus 3y. I don't look at the constants because, again, the goal is to eliminate one of the variables. So if I'm looking at the x's, I see 5x and I see x. Well, if I had a 5x and a negative 5x, that would allow me to eliminate the x's. If I look at the y's, I see a positive y, I see a negative 3y. Well, again, if these were the same coefficients on y but with different signs, that is, if I had a negative 3y here but a positive 3y up here, I could eliminate the y variables. So let's try and do that. Let's see how that plays out if I do this. I'm just going to try and do this quickly because I'm trying to remind you of how this works and then show you what this looks like in the context of quadratic systems. All right, so let's take this first equation. And what I want to do is multiply it by 3. So I'm multiplying 5x, y, and 8 by 3, which gives me now 15x plus 3y is equal to 24. I take my second equation, I'm not going to touch it, I'm going to leave it as x minus 3y. And again, the advantage of this is plus 3y minus 3y, that adds to 0. So I have multiplied them, my y's have the same coefficient but with opposite signs, so now what I can do is add these two things together. 15x plus x is 16x, plus 3y minus 3y is 0. You don't have to write 0, we typically just leave it empty because we know it's 0. 24 plus 24 is 48. So if 16x is equal to 48, I can divide by 16 and x must be 3. Well, at that point, I've done a substantial amount of work already towards determining the solution, the ordered pair that solves this system. So what I want to do with that 3 now is substitute it into either one of these original equations before I multiply by anything, and then solve for the y. I can use either equation, it really does not matter. If one of them screams at you to be easier, I would use that. If you substitute into the second equation, I just substitute in 3, and then I have to solve for y by usual algebraic methods. If I substitute into the first equation, I have to multiply by 5, and again, the solving will look a little bit different, but should produce the same solution. I will substitute into the second equation just because. So I have x minus 3y is equal to 24, but we now know that x is 3. So 3 minus 3y is equal to 24. If I subtract 3 from both sides of this equation, I will have negative 3y is equal to 21. Dividing both sides by negative 3 tells me that y must be negative 7. So the solution to this system of equations is the ordered pair 3, negative 7. For linear systems, this works rather well. For quadratic systems, the reality is sometimes this is really just not useful, and other times, even if you can use elimination to solve a system, it's generally just as easy to solve by substitution. So let's take a look at some examples of how we could solve this by elimination. This first one right here, I see x squared minus y is equal to 4, x squared plus y is equal to 24. Before I jump right into the how to solve this by elimination, I want to refer you back to what I just said. I could very easily solve this system of equations by substitution. X squared plus y equals 24, x squared minus y equals 4. If I solve one of these equations for y, then my life is pretty simple and I can solve this by substitution. I can take this second equation and say y is equal to 24 minus x squared, and then I can substitute into the first equation x squared minus y equals 4, and x squared minus 24 minus x squared is equal to 4. and I can solve this equation rather easily. So this is what I'm telling you. In almost all instances, yes, sometimes solving by elimination is useful, but generally speaking, it's still just as easy to solve via substitution. Anyway, sorry to interrupt myself again. How do we solve this system by elimination? Well, the idea is to eliminate either the x's or the y's. The way quadratic systems work, generally speaking, you're going to eliminate the y's. In this particular equation, it's not as obvious why. We'll see a better example of why in example 2. Alright, so let's take a look here. X squared minus y equals 4, x squared plus y equals 24. Well, I can see right here that the coefficients on y are -1 and +1. -1 and +1 have a sum of 0, so what I can do straight off the bat is just add these two equations together. X squared plus x squared is 2x squared. -y plus y is 0. Again, I'll write 0 just for emphasis, but we do not need it for anything. 4 plus 24 is 28. Now, I have 2x squared is equal to 28. Again, this 0 doesn't do anything. So what I will do is divide by 2. If I divide by 2, then x squared is equal to 14. Now, I can take the square root, and I must remember that anytime I take the square root, I need a plus or minus, and I get x is equal to plus or minus the square root of 14. Now, this is setting me up for two solutions. One with an x-coordinate of the square root of 14, and another with an x-coordinate of negative the square root of 14. I need to find the y-coordinates that go with each of these. I can use either equation that was given to me originally. It really does not matter. I'll use the first one for no particular reason. X squared minus y is equal to 4. Well, in the first case, x is the positive square root of 14. If I substitute this in, then what do I get? I get the square root of 14 squared minus y is equal to 4, which means 14 minus y equals 4. Now you can go through whatever solving you want to do that. If you think of this very simplistically, 14 minus what equals 4? Well, 14 minus 10 is equal to 4. Y is definitely 10 right here. How does this change if I put in the negative square root of 14? Well, you might be surprised. If I put in x is equal to the negative square root of 14, if I square a negative number, that negative will become positive, and what I will get here again is simply 14. So once again, I will have 14 minus y is equal to 4. And again, you can solve this by whatever means you want. We already know what y is. If you subtract 14 from both sides, negative y is equal to negative 10, which means y is positive 10. So my solutions are these two ordered pairs, square root of 14, 10, and the negative square root of 14, 10. And it's that simple. Let's take a look at a slightly more advanced example of solving by elimination. Right here, I see that I have 2x squared in both equations. I've got a 3x and a 7x, and then I've got a minus y and a minus 3y. Again, I don't really worry about what these constants are down here because I'm not going to be eliminating those. Now, I could try and eliminate the x's, but the reality is, since I have 2x squared and 2x squared, which is already the same coefficient, although I'm trying to get different signs in those, when I have the 3x and 7x, there is no way to simultaneously eliminate both the x squareds and the x's. You may recall, again, a few minutes ago, I said that generally we would be eliminating the y's. So that's what I'm going to do. I'm going to eliminate the y's because I can't eliminate all of these x's at once. Whereas I have only minus y and minus 3y. Well, if I take this first equation and multiply it by not 3, which would give me negative 3y, but in fact a negative 3, because if I multiply by negative 3, then I will have positive 3y, which will add with negative 3y to give me 0. So I'm going to multiply that first equation by negative 3. I will have negative 6x squared minus 9x plus 3y is equal to negative 162. The second equation remains unchanged. And again, I'm going to add these two together. What I will get is negative 4x squared minus 2x, 0 again is what I get here, is equal to negative 110. Alright? So now I have an equation, a quadratic equation, in a single variable. So what I will do here to solve this equation is move everything to one side so that it equals 0, and then attempt to solve by factoring, because that's going to be your primary means of solving a quadratic system. So if I do that, negative 4x squared minus 2x plus 110 is equal to 0. If you take out a negative 2, that's your GCF, you'll be left with 2x squared plus x minus 55 is equal to 0. Alright, so now what I need to do is factor this polynomial. If you know how to factor, then you can just go ahead and do that. You should be able to do that at this point. I'll show you the work right up here. So when I'm doing this, I need factors of 2 times 55 is negative 110 x squared. Factors of negative 110 adding to 1 are positive 11x and negative 10x. I group and get x times 2x plus 11 minus 5, times 2x plus 11. So I can see my factors are negative 2, x minus 5, and 2x plus 11. And again, this is all equal to 0. I did my factoring, but I must remember this was an equation that equaled 0. So then you take each of these factors, set them to 0, and solve. Negative 2 equals 0 gives us no solution. X minus 5 equals 0 will give us x equals 5. And 2x plus 11 equals 0 will give me that x is equal to negative 11 halves. Now, what I need to do is substitute these into the original equations, one of them, and solve for the y value. Now these numbers are not especially nice. 5 you can do fairly easily, but negative 11 halves is going to work out a little bit nasty, because I just didn't think of a better problem. I probably should have used something that the numbers would have not been so stinky. So sorry. Alright, so let's take a look at what happens when we substitute in 5. I'm going to use this first equation, 2x squared plus 3x minus y is equal to 54. Now, you can go ahead and substitute in like this. What I'm going to do here, because it makes a little bit more sense to me and will make my work a little bit cleaner, is to actually solve this equation for y by adding y and then subtracting 54. So then when I do that, 2x squared plus 3x minus 54 is equal to y. The advantages of doing this, as opposed to just purely substituting right in here and then simplifying and solving, is I will now only have to simplify. If I substitute 5 for x, what do I get? I will have 2 times 5 squared plus 3 times 5 minus 54. That should be the y value to go with 5. 2 times 5 squared is 25, so that's 50 plus 15 minus 54. So this right here is 11. So I have my first ordered pair. My first ordered pair solution will be, I'm sorry, I'm writing a little bit low. My first solution will be 5, 11. Now when I put in negative 11 halves, I have to be a little bit more careful. You might want to use a calculator if you're not very comfortable with fractions. But when I substitute 2 times negative 11 halves squared plus 3 times negative 11 halves minus 54 is equal to y. This is 2 times 121 fourths minus 33 halves minus 54, which is 121 halves minus 33 halves minus 54. 121 halves minus 33 halves is, 88 halves, or 44. So it's a fair amount of work to get there, but we ultimately do get a fairly simple answer. The y coordinate to go with x negative 11 halves is simply negative 10. So my solutions then are 5, 11, and negative 11 halves, negative 10. You could have solved this by substitution as well. The fraction, substituting that value in to get the y value, does make things a little bit more complicated because it's much easier to make a mistake at that point. But again, if you're careful, you should have no problem arriving at the correct answer. Again, I could have solved this by substitution. Right here, I went ahead and solved this equation for y. I could have done that to start and substituted this expression in place of this y and distributed -3 at the start. Alright, there's another example here. I will leave that to you. It's in your notes. What I want to look at now is the next page of these notes. And that is a system with no solution. What we can expect for quadratic systems, if you encounter a system with no solution, generally it will be via graphing. Not generally. On a test or quiz, it will be via graphing if there is no solution. But algebraically, I do want us to consider what does it mean for a system to have no solution. If I had linear systems, that is a system of two lines, there was only one way to get a system that had no solution. No solution meaning no intersection. And that was to have two lines which did not intersect, in other words, two parallel lines. And of course, parallel lines have the same slope, so that's very easy to identify. However, if I'm dealing with quadratics, I cannot talk about parallel quadratic functions. Simply speaking, it's just not defined to say that. So we should consider, what does this mean to have quadratic functions which, when put into a system, give me no solution? Well, let's take a look here. Here are two examples of quadratic functions where the system will have no solution. This first one, since y equals 2 times x plus 3 squared plus 1, and y equals 2 times x plus 3 squared minus 4, since these are both y equals, substitution tells me that I can say that 2 times x plus 3 squared plus 1 is equal to 2 times x plus 3 squared minus 4. Now, it's very tempting to simplify these expressions, square x plus 3, distribute the 2, and then add the 1, or on this side subtract the 4. But notice, these are both 2 times x plus 3 squared. So I can actually simplify this for myself and subtract 2 times x plus 3 squared from both sides of this equation. Well, what happens at that point? 2 times x plus 3 squared minus 2 times x plus 3 squared is 0. So what I'll be left with is 1 is equal to -4. I recognize that, of course, 1 does not equal -4, and this is an equation which has no solution. Graphically, what does this look like? Well, let's take a peek. 2 times x plus 3 squared plus 1, this is vertex form. I go to -3, 1, and I'm stretching by 2, so rather than going out 1, up 1, I go out 1, up 2. And rather than going out 2, up 4, I should go out 2, up 8, which will put me a little bit above this grid, gives me space to do. So I'll just get a general idea of what it looks like. Do your best to make it look like a parabola. I've missed my points a little bit, so this is not one of my better parabolas. This other equation, 2 times x plus 3 squared minus 4, well, the vertex for that parabola is -3, -4. And again, there's a stretch by 2, so I go out 1, up 2, and out 2, up, again, not 4, which is what I would normally do for an unstretched quadratic, but go up twice as far. Instead of going up 4, I will go up 8, which puts me right here and right here. And what I will see is these parabolas don't intersect because one of them is entirely inside the other. And again, I haven't drawn this parabola particularly well. If you graph this with a calculator, you'd see, again, that one is entirely inside the other. And you can see that they are getting closer up here. While they will get closer, they will never actually intersect. And I'll just say that without any real justification. They won't intersect. The best justification I can give you is this algebra we've already done. All right. So that's one way that I can see algebraically that the system has no solution. Well, what if I don't give you something that's this neat? What if I give you two equations, both in standard form? So let's take a look. If you graph these things, I'm not going to show you how to find the vertex of either of these. I'm just going to graph them. I'll leave it to you to use a calculator and do that, or use your knowledge of quadratics to graph these correctly. So x squared plus 2x minus 2, go to negative 2. If I substitute in 1, then I will get 1, and from that I can determine all this other information right here. And that's y equals x squared plus 2x minus 2. For the second equation down here, y equals negative x squared plus 7x minus 8. I want to double check my spacing here. Yes, that's where I want to go. If I put in 1, I will have negative 9 plus 7 is negative 2. And again, this one's a little bit trickier to graph. If you try and find the vertex, you'll find that the vertex is at, what does this appear to be? Looks like 7 halves and 17 fourths, I believe. Vertex is not very nice for this particular quadratic. Again, I'm using some math that I did not teach you, that I have learned over years and years of doing algebra. I know, it's very exciting. So I can see that these two quadratics do not intersect. Again, they get fairly close. They look like they might intersect when you first start sketching it, but then we can see that very clearly they do actually miss each other. Okay, algebraically, what's going on here? So again, these are both y equals, so if I set this up to solve by substitution, x squared plus 2x minus 2 must equal negative x squared plus 7x minus 8. Now this is a quadratic equation, which means I need to get 0 on one side in order to solve this. So what I'm going to do is add x squared to both sides. And I will subtract 7x, and I will add 8, and I get this equation, 2x squared minus 5x plus 6 equals 0. Now, what I would try to do, of course, is try to factor this. If I do try and factor this, I need factors of 12x squared that add up to negative 5x. Well, 12 does not have that many factors. It's 1 and 12, it's 2 and 6, it's 3 and 4. So with a negative 5, well, if I did a negative 3 and a negative 4, I'd get negative 7. Negative 2 and negative 6 would give me negative 8. Negative 1 and negative 12 would give me negative 13. There's no actual way to get a negative 5. This does not factor. And as you might recall, if a quadratic does not factor, your next step in solving would be to use the quadratic formula. Okay, well, again, here we have to think a little bit. What does the quadratic formula tell us? Well, we remember that when we learned the quadratic formula, which is x is equal to the opposite of b plus or minus the square root b squared minus 4ac all over 2a. When we learned this, we knew that b squared minus 4ac, this expression underneath the radical, was called the discriminant. And it told us certain things. Let's look at b squared minus 4ac, the discriminant of this quadratic. b is negative 5. A is 2, and C is 6. Again, these are just coefficients and constants straight across. A, B, C, include the signs. So this is 25 minus, because there's only one negative down here, 4 times 2 times 6 is 8 times 6 is 48. So this is negative 23. All right, so then we have to ask ourselves, well, what did it mean when I had a negative discriminant? A negative discriminant, and again, you can recall the quadratic formula, it's right there, meant that I had the square root of a negative number. The square root of a negative number means that I have non-real solutions. If I have non-real solutions, I cannot possibly have an intersection in the xy plane, the real plane. So here's the deal. Algebraically, what is happening when there is no solution is either a situation like the first example above, where What I had was an equation that simply, again, from an Algebra 1 basic understanding of equation standpoint, I knew this had no solution. Excuse me. Or what I could get is something like this, wherein I have a negative discriminant, which means there are no real solutions, which means I cannot possibly have any intersections. And when we're solving a system, that is what we are looking for. We are looking for points of intersection. So for our standpoint at least, this system has no solutions, and that's what the discriminant is telling us. Again, in some more advanced class, you could potentially look for the complex numbers which do satisfy the system of equations. But that is outside the scope of what we are doing. So, please be aware. To show a quadratic system has no solution, what you would generally do is graph to show that there is no intersection, and or algebraically show that there are no real solutions by using the discriminant. Are you going to be asked to do this on a quiz or test? In all likelihood, no. The point of me showing you this is more about you understanding than anything else. All of math, remember, comes down to understanding. I hope this has been helpful.